Hello, everyone. The professor Rukunye well explained and detailedly explained what's the hypertrophic cardiomyopathy, what's the HCM, and what is the the flow structure in the left ventricle. Just to refresh your idea, the hypertrophic cardiomyopathy is a genetical heart disease where the heart wall become abnormally thick, especially between the septums. And when the walls become thick and this patient has, the wall is not the contract well, and it's become like much more stiff, so it drops the cardiac output. And if the left ventricle, the grow asymmetrically, and then they block the left ventricle outflow tract, and then that patient called as obstructive hypertrophic cardiomyopathy. And CMRI images is the gold standard imaging techniques for the HCM diagnosis. It has like the 3 axes, the 1 short axis and 2 long axes. And each axis has the 20 frames per second. And it can also provide the geometrical information. We can do 3D segmentation out of 3 axes. We can see the 3D segmented geometry for first time step out of the 3 axes. And then this is a combined version of this 3 segmented geometry. However, it is not suitable to use any kind of hemodynamic application. We have to do smoothing and reconstruction operation. After the reconstruction, all 20 different geometry has the 20 different the point information. So we cannot track them over time. To solve it, I'm just taking the initial geometry, and then I projected those points on the next geometry, the surface, on the normal direction. And with that way, we can follow the particles over time, because like all 20 geometry has the same point information, and then we can track it, and then we can use that. We can calculate the displacement, and we can use it as a boundary condition for our fluid structure interaction analysis. And here we can see all the track point over time with the displacement. And here I use the one-way fluid structure interaction analysis, perform all the CFD calculation. And I use the ADINA finite element solver for structural part, ADINA CFD solver for the fluid dynamic part. This is one-way FSI analysis. There is no any information sharing, the physical information sharing between CFD and the structural part. The CFD part solved Navier-Stokes equation in the fluid domain, in the initial part, and then just update the time step. The structural part take that time step, apply the displacement, and then get deformed geometry, and then share that deformed geometry with the CFD part. CFD part take that deformed geometry and update the meshes, and then that cycle moves like that until it ends. Here is the finite element setup and CFD setup. On the finite element setup, we are the FSI interface surface and showed with the yellow surfaces. And the pink dots represent the displacement boundary condition over time. And the green dots shows the fixed boundary condition. In the right side, for the CFD side, we see 3 different fluid domains, and that the green surface shows the fluid structure interaction. The surfaces is going to interact with the structural part. And here, this is kind of like the simplified model. I didn't model the aortic valve and the mitral valve. Instead of modeling it, I use the flow, the boundary condition. It's called as the gap boundary condition in the ADINA. Actually, it's generate the connection between the one fluid domain with another fluid domain, and then it's controlled with the time function. When the time function is 1, it's gonna allow the fluid flow from one domain to the another domain. If the time is 0, it's gonna, close the connection between one domain and another domain. It's gonna simulate the opening and the closing the valve. Of course, it's not going to be like the exact valve opening. It's going to be sudden opening and then sudden closing. You can also see that effect in the flow. And this is the classical Euler method that shows us the velocity magnitude and the velocity vectors. And then it can also give information about some kind of the rotation. However, to better understand the exact flow and disturbed flow in the left ventricle or the HCM or OHCM case, we have to do additional calculation. And the Liutex magnitude is a powerful tool that directly shows the vortex course, and that calculation done by Dr. Liu, Mariam, and Oscar. In the left side, we can see the 3D isosurface view for the Liutex magnitude. And the right side, I just add a mid-plane on the 3D geometry, and then I just draw the contour. Because like this is much more easy to understand what's going on inside the ventricular. And if you look at the HCM cases, this is hypertrophic cardiomyopathy cases, we can see the one developed, right now. You can see like the one developed the vortex course, it's moved middle of the left ventricular, and then second one is developed. Of course, I'm not modeling the valve, and we cannot see a valve effect. If there's a valve, it must be kind of like the vortex structure. And that vortex is developed by the sudden expansion on the edges. And if you compare the HCM and the OHCM cases, we see here like the vortex structure, then the right one. And here, there's like the vortex structure is generated because of that sudden expansion on the edge. However, it's really weak and it doesn't move through the left ventricle. Okay, we got some idea about how the vortex is generated, and then that gives some idea about the disturbed flow. But the detailed understanding, the better understand what's going on inside the left ventricle. And because the particle washout and the mixing and the stagnation zone is really important for us, so I use Lagrangian coherent structure analysis to track the particle. And the first, I put the Z-plane on the 3D geometry, and then I extract all the grid point and the velocity information onto that plane. If you look at that one, they are not like the fully aligned because I used the tetragonal meshes. This is not the perfect structural mesh. And so I just, interpolate that result and generated grid. So I just create a boundary box, and then I created that boundary box according to biggest volume of the left ventricle, because this is 4D geometry. It's moving over time. And I generated the structural grid. Then I interpolated that velocity value on the structural grid. So I have the structural grid on the interpolated velocity value. And then the LCS, the first part of Lagrangian coherent structure, is the particle tracking. For the particle tracking, we have to calculate the flow map. It's here. It requires the velocity and the position and the time data. And I use the RK4 Ranji-Kutta, the ordinary differential equation solver, to calculate that one. And it just takes the initial point of the particle, and then it just calculates the next point. With that way, we keep going on to that calculation. Over time, we can track any injected particle in the left ventricle. Okay, that gives us idea about how the particles moves inside the ventricular. With that way, we can calculate the stagnation zone. We can see different flow separation lines. We can also see the particle washout and the mixing. But if you want to see coherent structure, we have to do additional calculation. And here, I use the finite time Lyapunov exponent calculation, and it starts with calculating deformation gradient tensor, because it just interested in the maximum stretching. However, the gradient tensor has the stretching and also solid body rotation, and we need to remove that solid body rotation. So I calculate the right green, the strain tensor, and then to get the maximum eigenvalue, to get the maximum stretching. And then this is the formula, 1 over t ln square root the lambda max. This is absolute value t, because this is the integration time step, it's not our analysis time step. We can choose the integration time step, how far we want to track the particle for analysis. And this is the result for the backward finite time line point of exponent result. The solid red line show the pure stretching on the flow, and also they show the separation line. If there's any flow particle located in any side of that line, the meaning of that particles cannot move the other side. And this is the pure stretching, so it cannot detect the vortex core, but it just shows the vortex, the boundaries. And if you compare the HCM and OSM cases, the HCM has like the big and the solid, the FDL lines moves middle of the left ventricle. However, the OSM case has small and short, the stretching line. And with the particle analysis, we can look at the particle washout. This is important for the left ventricle because we every time want the fresh blood inside the left ventricular, it must be, the replaced with the new blood, with the old blood. And with the particle analysis, I just add the black particle at the time 0, and then I track all particles for 3 cycles. If you look at the particle count over 3 cycles, in the HCM cases, only 8% particle just remain. On the right side, 31.3 particles remain in the ventricular. It's not a good sign. It shows that many particles stagnate in the left ventricular. It could be because of the thrombosis or some kind of problem. And that one, I just performed that analysis to see the cycle effect. The black particle injected at time 0, the red particle injected during the first cycle, blue for second cycle, the green for the third cycle. With that way, we can also see how the particles react over time, over the cycle. We can also see, these are actually the high stretch line, and we can see how that stretch line, the compress in some location of the flow, and we can get the main idea how different cycle particles react each other. At the right side, same. After different cycles, I'm injecting particle. Still, I see many of the initial time 0 particles in the apex. And that one is a combination of the Liutex and the Lagrangian coherent structure analysis. Here, this is 3D. This is the section plane result, FTLE and combination of FTL and the Liutex. If you look at here, you see the FTL just show the pure stretching and the vortex boundaries, and we can see that vortex just starts from here and then moves with the stretching line. And you see, just like the moving here, and then if there's any line, it cannot pass the other side of the line, or here also. If any vortex generated here, it cannot pass the other side of the line. And so we can also see with that way how the vortex cores use the path and then move through the left ventricular. It can also show the vortex path inside the ventricular. And if there's any, the high backward FDL line, drawn until here, the meaning of that the vortex generates from here and then moves up to that point only. You can also see here. And that one combined all the power of the particle analysis, the Liutex magnitude, and the maximum FDL line. And with that, we can get a better idea how the vortex are generated and how those vortex disturb the flow, you see, and how the FDL generate a boundary between the vortex and the other particle, and then how the inflow, the fresh particle and old particle, react each other, and then how the particle washout perform with the vortex. If you look at the right side, we don't have any, big vortex cores, just like located in the apex, the outflow tract area. It cannot even move to that part, so we don't see any disturb or the mix or the particle washout here because of the weak vortex structure located on the outer axon. As a conclusion, the Liutex is a powerful tool to show the vortex core, and LCS is another powerful tool, gives us the many idea about the flow and flow boundaries, stagnation, the layer, the cycle effect. And if you look at the left side, this is the apical thrombosis. The patient has a thrombosis in the apex site. With combination of the Vortex course and the FDLE, we can also get idea why those people has apical thrombosis. And then that could be a way to understand and to make a relation between thrombosis with the Vortex and the flow separation lines or any other disease. This is just simplified work. We are working on the much more complex analysis that gonna represent the realistic and the physiologic flow in the future. And then we can also increase the number of the patients. Okay. I want to thank my Professor Sandra and my lab mates and our collaborator from the UTA, UCSF, and Medivita. Thank you for having us.
Great, thank you.